No, okay, so hopefully everybody has a badge now. So this meeting is going to be on microcontroller programming. So like how can we compile and run code on microcontrollers. So like the Pulse ETF badges that you all have, they run an ESP32. That's a microcontroller from this company called Espressif. So I guess before we get into like the technical stuff, some short like intros. So I'm Nikhil. I'm an admin at SIGPwny. I've been involved with the club since my freshman year. I'm a computer science major, and this summer I lived in Columbus. I'm sorry I don't have anything more interesting for you as a fact.
So hi, I'm Krishna. I'm a SIGPwny helper. I'm computer engineering class of 28. And my fun fact is even less interesting, which is I'm from the DC area.
Yeah, so I think these slides should be up on the website. Jake, are they up?
Yeah, they're up.
Okay, perfect. So you guys can follow along, like if you ever need to go back to a previous slide for some instructions or something, that you can find up there.
Also, there are a lot of like commands, so it might be easier to copy paste them if you have the slides.
Yeah.
Depending on how advanced you want to get with the programming, some of the commands get a bit long, so might be helpful.
Yeah, so I think so let's start with like what is an embedded system. So we covered this during the last meeting, but I think it's helpful to kind of review that a little bit. An embedded system really is like a small computer. It has all the parts of a computer. It has like a CPU, a processor, it has memory, it has some kind of like persistent storage like flash that is kind of similar to like your hard drive. It has some input-output devices. You can print things to like some interfaces, like serial interfaces, things like that. You can get inputs from like sensors or like different kinds of pins, or that sort of stuff. So really, I mean, it's a very kind of simple computer. They're supposed to be usually like low power, low resource, small kind of form factor and so on. Because before we move on, does anybody have like any questions about like what an embedded system is or why like why we care about that? Okay, perfect. So embedded systems we program usually at kind of a very low level. An ideal language for doing that is the C programming language. So C was invented in the 1970s, a long time ago, for developing the Unix operating system. So if you run Linux, Linux is a descendant of Unix. When creating Unix, the creators of Unix found that no programming language that existed at that time kind of met all of the requirements, and they invented C for this reason. The C is ideal for low-level programming because it was essentially created for doing this kind of thing. So you can get direct access to memory, direct access to hardware, peripherals, and things of that sort. And that makes it very useful for programming microcontrollers. And like even like later on, maybe we will look at some Rust programming. And like Rust also has many of these same features, which is why you do that. So yeah, right. So C is a compiled language. What this means is that when we write code in C, you have to put it through a compiler, which translates it into assembly. The assembly is what actually runs, like assembly is like the binary code, essentially ones and zeros that run on the embedded system. So like, I guess pop quiz, does anybody know what architecture is like used commonly, or what architectures are used commonly in embedded systems? Yeah.
Usually they're ARM.
So ARM, yeah.
Also, RISC-V is becoming popular.
Sure. Yeah. Yeah, MIPS actually is interesting thing. MIPS used to be very popular, not as much now. I think like game consoles use it or something. Does anybody know what architecture the ESP32 uses? Like the one that you're running?
Is it ARM?
I think it's Extensa.
It is.
Yeah, it's Extensa. It's like their own ISA. It's like similar in ways to ARM. So, I mean, the point of like knowing about this is that when you compile a program, it depends on what architecture you're compiling it for. So the same program can be compiled for different kinds of architectures. And like when we do embedded systems programming, we will compile for the target architecture of the device that we're looking at. Like when you compile for your PC, like you're compiling for your PC's architecture. So I guess we can look at an example of what compilation looks like. So this is ARM. This is a very simple program. It's written in C. It adds two numbers. It prints the result. This is what the assembly code looks like that gets generated when you compile this. So this is basically what is running on your system, essentially, on your embedded system. So like later on, we will try to compile a simple project and run it on the board. And like when we do this, the first step will be to convert the source code into assembly or into binary. And then of course we have to somehow send that binary over to the device. So like somehow this code has to end up on the actual board. And to do that, it's converted into basically a stream of ones and zeros that is sent over like USB or wherever to the board. So like later on we will like flash the board. Like when we flash the board, what it means is that we are taking this compiled assembly code and we are sending it as a stream of ones and zeros. Thanks. Any questions so far? Yeah. Okay, so now we will kind of do a hands-on walkthrough of flashing your false ETF badges. So we will be using this thing called the ESP IDF, the IoT development framework that like provides a bunch of tools that help you program these ESP32 devices. So yes, that's some like high level. What do we need in order to flash a board? Well, we need somehow to compile our code. And that process is handled by like what you can call your toolchain, which contains compiler, linker, like all of the components that help you turn your source code into binary or assembly. And we will use the Extensa compiler. The Extensa is the architecture on these devices. We will use the Extensa compiler that is provided to us by Espressif, which makes these boards. We need also like the compiler is kind of like a simple thing. It takes an input source file, it produces an output file, an output assembly binary file, like encoded as binary. If we have kind of a large project with a lot of different moving components, we need somehow to like orchestrate the compilation of the different parts of the project. And to do that, we will use a build system or like a build tool. I mean, this is like something that's used like everywhere and like computer science. Like if you've used make files, like that is basically what that is. Like if you program in Java, like there's build tool, there's like I think Apache Maven, stuff like that. So we will be using CMake, which is again what the Espressif, like their framework uses. And then we need some way to take our binary code, maybe something that looks like the assembly that you saw previously, and like put it onto the device. And we will do it through again through IDF. IDF internally uses this thing called ESPtool, which is like a program basically that helps you do a bunch of different things with these boards. Like you can look at the source code of ESPtool if you're interested. See like what does it actually do.
But yeah, key point is the IDF handles all of these.
Yeah. So like you will not see ESP. I mean, you might actually see IDF like printing out the ESPtool commands that it's running. You will never have to actually run ESPtool yourself. Okay, so let's get started with this. So the first step is to install IDF. So they provide this as a VS Code extension. Does anybody here not have VS Code? Okay. But if you have VS Code, like go to the extensions, so I can kind of demo this. So go to the extensions like manager, and if you search up like probably Espressif, the first result should be the expressive IDF. But we can. This is the extension that you want, the ESP IDF for VS Code. I guess, yeah, let me know if like you're having any trouble finding this or installing it. Yeah. Oh, the badge, yeah, sure.
I had to use this tools, I had to hold.
Yeah. Do you want?
And once you install the extension, what you'll want to do is click on the Explorer thing over here to the left.
Right.
And you'll only see this, but you should click the Configure ESP IDF extension.
Yeah. Next step is we have to like download. So this extension like gives you the kind of overall like framework for dealing with the IDF environment. Like we have to actually download their toolchains and stuff. So you want to click configure ESP IDF extension. When you do that, it should pull up, hopefully, it should pull up something like this. And we want to choose the express option. What? It is very fancy. So like it is actually very like in the grand scheme of things, like this is actually not bad. Like
It's not bad. It's
pretty good.
I mean, compare this to.
It's not
some
hard,
arcane documentation, like.
yeah.
Yeah.
Usually you
Yeah.
just go to the site down.
That was written in 2006.
Yes. So if you click on configure ESP IDF extension,
You'll see this thing.
yeah, that should pull up something like this. And was everybody able to like find the express option? Yeah. Okay, so when you click on express, it will ask you to like select a few options. So keep your download server to GitHub. So you should select ESP-IDF version to just like select the latest one. It's 5.5.1. And like the rest is like where it actually installs things into. So I mean, you can leave stuff by default. If you want to change it, then you can change it. It needs Python to run. So you have to give it a path to your system's Python, wherever that is. So like on Linux, it's probably in user bin Python 3. If you are on Windows, I don't know where it will be, but
Actually, it doesn't add your path.
It doesn't?
Windows doesn't ask because Windows would just use the path.
oh, it just use, okay, sure. But yeah, the like actual like they have so this IDF, they have this IDF.py like all-in-one Swiss Army knife script that will do everything. And it's a Python script. That's why they need Python. And once you've selected all of this, you can hit install. It should probably take a few seconds to work. But yeah, we'll wait for like 5 minutes. Yeah, and I guess like feel free to like raise your hand or something if you're having any. Yeah. Version like just take the latest one. No, I don't think like the super pop.
I mean, it's not stuck, but like, you have a hacks romance, bro.
Do you have like the first right?
Unsupported,
But what did it say? No, I'm using their commands. Because I am not pushing the public. Right?
What do you use here?
Plus, they have.
Yeah, this link, by the way, also helps. In case you don't have VS Code or something.
If you're very talented, you can probably figure out some web plugin. Like, you
Wait,
probably-
literally?
But like I would not recommend it right now. You can do it if you want.
Damn, they did. Like, excuse me. Yeah, or me. But it's not getting crazy.
Can you try uninstall the yeah, and then we start to kind of maybe find like close one. Try if it doesn't work, then I can find you some like crash videos too. Okay.
I'm too.
Allison. What?
I'm too.
No, I didn't stop. Oh. I had. That's so real. I have to do it.
I went home to grab it.
I have them. They're just fine.
It's very yellow. Yeah, like it took them out, I was back for like the first time in like 6 months. Yeah. I just biked up and went back to the I thought it was dirt, but I think it's just like. Yeah. I mean, it's only one more. It's, no, you're not gonna get.
I didn't know.
By definition, once you have enough answer, you get more answers.
Oh.
Sounds like
No, mine's still.
Yeah, I'm like, I could be installing malware right now.
we're already sleeping. I sleep schedule's even more.
I'm so stupid.
Hey, you brought it on yourself, you're not allowed to.
Yes, I woke up at like 1 AM. Like yesterday. But I slept at like 5 PM. I slept that, and then I woke up at midnight.
So we're like.
Stayed up until 8 AM, and I slept at 8 AM, and I woke up at like.
Oh, so it's like.
You sleep like 3 times a day, basically.
No, it's not like
3 hours.
It sounds like it's getting better and better.
It does not, it really doesn't. Okay, we should continue.
Okay, does everybody have the extension configured? Any issue? Okay, so Right, so what this has done is that this has now downloaded all of the ESP like toolchains and all of their software. So we can now use that to compile and like flash our code. So next step is going to be to fetch one of their example projects. So you should go to show examples. And like just use this default path that it gives you. And you should find this hello world example. So yeah, I guess if you're having any issues finding the example, let me know.
Yeah.
Sounds solid?
Yeah,
How-
I'll take it back.
The
Okay.
install times are pretty long.
Okay.
What?
Sure.
Like
It's still
opening the-
installing for people.
It just takes like 5 minutes.
5 minutes?
Yeah, I started installing right when you said.
Yeah.
We'll give you some time to install, and it finished about like 2 seconds, right? Right.
Okay. Okay, I guess we'll wait for a few minutes.
Takes a minute.
But yeah, if it's like once it's done installing, you can try like opening.
I guess you could say it's especially slow.
Yeah.
Wow, very, very good. Faster than most of those sent who's gonna download it, so. I'm not sure if that's a more of each thing, but I download four things. How's your week been?
It's been all right.
It's been all right,
Kind of busy.
kind of busy.
285 report, this.
I was going through a math derivation, and I looked at this guide, and it's at 100 steps.
Good job.
And I was like, wow, very good.
Very good.
And then it's written as like, and the professor was like, it's simple algebraic.
Very simple. Trivial even.
Yeah. My observation.
What's that sound?
Okay, does anybody still install?
Raise your hand if it's still installing for you.
So, but oh,
It's 1.32 gigabytes.
1.32
The
gigabytes?
repository itself.
Yeah.
Yeah, that sounds about right. So with this like embedded like tooling, like they will make you install every possible like piece of code, like binary, everything that you would ever possibly need. Like there's like no way to install only the things that you want.
There is, if you use the terminal.
No, I think for this, I don't know.
Well, I mean, you can choose the specific architecture you want to compile for, that's how it is.
You can get like all of your compilers like manually,
Yeah.
but that will take you more time than installing. Probably.
I thought the whole point of this like repository was that it has an orbit like in one place.
Yeah, but it
Yeah,
still has to
no, but-
install them.
We should be able to like
compiled. Well, yeah.
Think of it as a wrapper. It's like a wrapper script of all of those.
you should be
It's
able
like, it's like a mix.
I think you should be able to like select what you want. Like you
oh, how's that? So that's
This is going well.
going on.
There's a reason my laptop is not here.
Very good.
That's why you always gotta have two. You gotta have the Linux laptop and you gotta have that.
If only they had, if only we had 25.
Both my laptop and PC run this.
If only we had $25 thing kind of. Did you, wait, were you kidding? You were, They got bought out for $25.
I doubt this share is working properly, by the way, because you opened
like is there
VS Code.
anybody on to?
No, but it's recording.
Oh yeah.
We're gonna get a framework at some point. Winter break probably.
Which just
Don't remote
Yeah.
desktop. Wait.
It's
No, I'm sharing the whole desktop instead of
It's-
them.
like, it's $1,000 for like an okay model. Right, cause I'm not gonna be doing anything crazy on it. Like, I'm not gonna be playing.
Okay, you're gonna have to fix that again when we go to the slides there.
The most AAA games. I'm not gonna be playing any of that. So
There's like a longevity of it.
yeah, because like it will last.
Okay, raise your hands now if it's still installing.
Until he does the universe.
It's still alive.
Are you installing 5 out of 3?
I'll have this.
Mine might be right pretty fast.
I mean, yes, then I'll buy more RAM.
Well, maybe.
I'm wondering if like.
No, I don't need to do anything that. Because like, okay, look, if I need to run the auto, right? So the other thing I want to do is I want to make it so I don't have to like download any of the fucking, or I don't have to use the fucking stuff. Maybe that's the main.
Oh yeah, I guess like that's the
Next step is
You're gonna get breath. So where was
Plus, like, okay, so like, I want to play Elder eventually, something.
or like not.
But yeah, like I'm not gonna, I mean, look, 30 FPS and like okay graphics is enough. You don't need all the fucking 60 FPS is nice.
Okay, so we are going to skip ahead, like while this stuff compiles, we will skip ahead to some, I guess, theoretical like material on how embedded software works. So we will skip all of this for now. Okay, so this is a diagram I found on Google of the embedded software stack. Like I don't actually fully agree with this, but it has most of the major parts. So when you're writing code for an embedded system, there's like different levels of abstraction you can work at. So one level of abstraction is that you are directly talking to the hardware. It's like the code you run is the only thing that's running on the system. And like literally the processor executes your instructions one at a time. Like, and there's no other code, no operating system, nothing like that. And that's like what we call bare metal. So like in ECTF, if you play or participate in that, like our code will be bare metal. It will not be running with any kind of operating system, or at least it has not in the past. Even if you do that, like it's quite annoying to actually have to talk to the hardware. Because if you have ever looked at like a data sheet for some peripheral, there's some complicated like protocol you have to follow with the peripheral to like get anything done. So like you're gonna print a single character, like you might have to do some kind of back and forth with the UART peripheral. So to make our life easier in doing that, we have this thing called a hardware abstraction layer. I don't know why this is not abstraction layer.
ATM machine.
Yeah, but HAL stands for hardware abstraction layer. It does exactly what it sounds like. It abstracts the hardware. So instead of like write this bit to this register of the UART peripheral, you are kind of working at the level of write this character to UART. And the library will handle for you all of the low-level details of talking to the hardware. So so that's one layer you can work at, where you are still like there's still no operating system. There's no like multiple threads or anything like this. But you have this kind of abstraction library that's included within your code. So like it's in, you have to like link it with your own code that you can use to talk to hardware. And like that's exactly what we do in ECTF. You also have this thing called an RTOS. So that means, okay, does anybody know what RTOS means?
Real-time operating system.
Yes. So what is a real-time operating system? It's a very lightweight. So I mean, remember, like in an embedded system, we care for things to be lightweight, right? Like we don't want to put, usually at least, we don't want to stick like all of Linux onto a microcontroller. Like I doubt it will even run very well. I mean, there's like embedded Linux, but usually for microcontrollers, like maybe it's not such a good idea because there's a lot of overhead and like you don't need most of the features of Linux even when you're running on a microcontroller. So what does a real-time operating system give you? It gives you a very small set of features, and it's kind of very minimal in its footprint. So you can do multi-threading usually, so you can have like multiple tasks or threads. You have some synchronization that you can do between these. Like if you're taking an operating systems class, like you probably know about like what a mutex is or like what a condition variable is. So you can get these kinds of features. You can get some memory management. So again, when you're running on an embedded system bare metal, you have no memory allocation, like all of that you have to write yourself if you want to, if you need it. All you have is access to like direct physical memory. So an RTOS will sometimes give you some kind of memory management features. And that's usually basically all that it gives you. And the real-time part in the real-time operating system means that it has some kind of timing guarantees. Like it's good for applications where things have to be done. I don't want to say very fast because that's not quite what real-time means. What it means is that you get a guarantee on how fast it's done. So maybe it actually takes some time, but you get a guarantee like the system will not just hang. And that's quite important in like various applications where you're running embedded systems. Like if you're running an embedded system inside a car, like you don't want the engine controller to just hang at some point, right? Like when you're driving. Maybe it's fine for the engine controller to run not at like nanosecond speed, but you need some guarantee on how fast it runs. And that's what a real-time operating system gives you. We also have this middleware, which is like assorted code, like it's not very important. And like I don't think you will ever see it very much, but yeah, it's you can have it. And then the application programming interface is like the API is like the interface that the RTOS gives you to use to write your code. And then on top of that, you can write your own application. And your application is like whatever you write. So like what we will be using today, we will be using an RTOS and we will be writing some application code on top of the RTOS. So now the part of this diagram that I don't agree with is this drivers that's in here, because like what do they mean by drivers? If there is a how, then what is the point of these drivers? I don't know the answer to this, so maybe you do. I just think maybe it's not correct, but who knows? Yeah.
I think I know the answer.
So yeah,
The chart would be the
maybe, but like it doesn't really make sense to put drivers below how. Like maybe on top of how I could buy it, like if you have some higher level abstraction of your hardware, but certainly not below how.
But have you considered that it makes the rainbow look better?
It does. It does. Maybe that's why they do it. Yeah.
Okay, so now going back to like the ESP and how that works. Okay, we're gonna start with over here on the left. So when you got those badges, either now or during fall CTF or whenever, you see the like connect, upgrade the screen. We programmed that, not we, but like SIGPwny programmed that using Python. Now you're probably thinking, how's Python running on an embedded system? The answer is something called Micropython. So Micropython is basically the program. Over here, it is the application code, or kind of like the RTOS in a sense. It runs on top of your hardware to allow you to run a Python program on top of it. So you install Micropython to your embedded system, and then you tell Micropython to run a Python program, and it's going to run the Python program like it would run a Python program in your machine, which is it doesn't compile the program, it just goes step by step. So that's kind of how it started. Now, the key point here is that you start with a stage 1 bootloader. So your ESP has, in some areas of memory, it has a stage 1 bootloader. And how this works is as soon as you plug in the ESP, it's going to start running that code. And it's like hardwired to run that code. So as soon as you plug it in, there's like a pin, a reset pin, and all of that goes in, and it starts running the stage 1 bootloader. And then once the stage 1 bootloader runs, that's important because it sets up like some of your like register values, memory values, figures out some of the basics that are going on. It then transfers control to the stage 2 bootloader, which is what Micropython runs at. And then that calls your Python program. So now in the middle, this is what we're going to be doing, is we're going to be flashing the board. And what does flashing the board mean? It means replacing the stage 2 bootloader. So we're going to be replacing Micropython with free RTOS, which is the real-time operating system. And then we're going to be writing a C program that goes on top of it that also flashes onto the board. So now when the stage 1 bootloader ends, it calls free RTOS instead of Micropython, and that's going to run the compiled C code that we compiled earlier using those tool chains that we also upload to the board. And now option number 3 is bare metal, and Nikhil touched on this a bit earlier. But bare metal is you don't have free RTOS. You're running your code directly on the hardware. Stage 1 bootloader runs for like a little bit, and then it transfers control to your program. So you're responsible for how are you manage memory, how are you going to deal with processes, what are you going to do? That's all your program.
We actually want to make a correction. So the current badge right now, this stage, we actually do use free RTOS. So what's actually happening is we have RTOS in between after the stage 1 bootloader, and then it runs MicroPython, and then it runs the Python program. So with all these layers of abstraction, and I actually mentioned this in the last lecture, but with all the layers of abstraction, it actually like increases the memory usage a lot. So, like there's this really goofy thing where, if you don't immediately allocate memory, there won't be enough room to allocate memory for display. And so if you try to do that, like the board will crash. And so what you have to do is you have to like allocate a lot of memory at the very beginning to make like a buffer for your display. And again, because everything is going through RTOS, it's like you can't manage the memory directly, so you have to work with what the RTOS gives you in terms of memory. Which is a little bit difficult when you're working on such a limited amount. So again, there's advantages and disadvantages to working with these systems. But again, the reason why we went with the MicroPython route is because it allowed us to develop the badge application program a lot faster. And that's like why we have the cool game, things like that. But just correction on that.
Is there a reason we run MicroPython on free RTOS? Because my understanding is you can run
So,
MicroPython here.
Yeah, you can run MicroPython directly. I'm not sure why we decided to use free RTOS. MicroPython on top of free RTOS. So I wasn't involved in that stage of that stuff.
Okay. It means that you every time you want to flash free RTOS every time. You have to build it.
Somewhat. So I'll
Actually-
get to that.
So FreeRTOS is linked into your code. When you
It is part of your code, basically.
Yeah.
Okay.
And this is how. So stage 1 bootloader, this is kind of like in words explanation of the graph from earlier. Stage 1 bootloader, the thing that first runs is going to run, I believe it just like memory address 0, but I might be wrong. It's hard coded, it's read only, cannot be modified. If you modify it, you're probably like breaking something if you like try to modify it. Once it finished, it jumps to a fixed memory address. So if you've taken like computer architecture or those classes, this might sound familiar. It's going to jump to this specific memory address. It's going to say, no matter what, I'm done. I'm going to go here. There better be code here for me to run. And that's the code that you put in with your stage 2 bootloader. So you're going to take the stage 2 bootloader, whatever it is, FreeRTOS, MicroPython, your own code, whatever, and you're going to put it at this memory address. And again, the script will handle this for you, but that is what goes on in the background. It's going to put it right here. Here's from the MicroPython docs. This is where I actually got the MicroPython running at stage 2 or whatever, instead of under FreeRTOS. Is you can see that MicroPython, when you install MicroPython to your board, it's going to tell you to write MicroPython itself to that memory address. And this command is very powerful. It just lets you write whatever you want over here at whatever memory address you want on the flash of the microcontroller. This is ESP tool, which I was talking about earlier. So in essence, to run a stage 2 bootloader, you just write it to a specific memory address, and then when it boots up, it's going to run that through the stage 1 bootloader. Now, if you're using FreeRTOS, which is what you guys are installing or hopefully finished installing by now, FreeRTOS is going to install at memory address 1000, and it's going to read memory address 8000 to figure out what the user program is. And the user program that we installed just defaults to go at address 10,000. And so in address 8000, it's going to say, hey, we have a program at address 10,000, you should run that. And then it's going to jump to address 10,000 and run whatever code you write. So the user program is flashed to address 10,000. So when you flash to the board, what you're doing is you're flashing FreeRTOS to address 1000 and your code to address 10,000 at the same time.
Wait, can you
Yeah.
explain a little bit more about like what do you mean where are we storing the list of flash?
It's some weird format.
Where's the question?
How are you storing the user programs at 8,000, right?
So I think actually my understanding of FreeRTOS may be wrong, is that well, perhaps this is one way to do it. Another way to do it that I've seen is that the user code and FreeRTOS are compiled together. And the user, so the like startup of your program is basically you like there's a function that FreeRTOS knows about that is the startup of your program, and like in that function you can like create different kinds of tasks which contain your user code. So like one way to think about it is that FreeRTOS plus your source code together is what is Underboard. So like maybe not separately, but they're compiled as one thing.
Yeah, this is kind of internals of how FreeRTOS works, not more so like stuff you have to know.
Yeah. So and in general, like that's actually a difference between how like a desktop operating system works, where you have like a program loader. You have the concept of the loader that can load a binary and start running it, right? Like usually in an RTOS environment, you have to declare all of your tasks or programs that you're going to run when you're compiling your code, and like that's all of you get. So you cannot start loading more things externally onto the board.
Yes. And that like when you like compile your code is when it figures out what to put in this region. Because again, you can have multiple programs that like RTOS can interchange between. And so that's why this exists, is so you can say you can put multiple programs in there, you compile it all together. The tool that you're installing is going to figure out what to write here. And then FreeRTOS is going to manage your programs the way you configure it. Okay, so yeah, okay, we can do this section later.
Is everybody done installing? Okay. Anybody? Yes.
This still installing this is not about installation.
Yeah.
Pretty big program is like saying X1000, X10,000 stuff.
You're asking like how big is our programs? Like usually
Like how many big memories?
how many bits is the
4
memory?
kilobytes, I believe.
What? 4 kilobytes?
I think Flash is 4 kilobytes.
I don't, it is on this board, but like it's measured in usually kilobytes to like low numbers of megabytes maybe. Flash, and you have RAM also, which is usually more, but.
It doesn't show. I believe it's 4 kilobytes of memory you have total.
Okay, so if everybody's done.
16
16
megabytes?
Whoa. No, looking at up to give me one. So we would to what's that? It's not kilobytes. It's probably 4 megabytes.
Yeah, that's actually.
Okay. 4 kilobytes is a little too low.
Okay, so if everybody is. Okay, so everybody's done installing, the next step is to get the example project. So, yeah, if you go to, how do I, okay, yeah, if you go to like show examples, hello world example, this should open up, and then you can, click on the select location thing. And like it will open up your file explorer, and you can just have the project set up in whatever location you want. Yes. 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 Like a big and then like.
Okay, I press sure it's in the stick one right.
Actually, wait, aren't already.
I think that's.
I don't know what. Like, look at that. Did it show like an error? Oh, wait, no.
It shows, so it's just saying yes, yes, what is that, yeah.
This thing. Oh, yeah.
It's actually just like
Like.
Hello world. Yeah, like search up hello world, or just hello. And then you know, hello. Yeah.
Okay, does everybody have the example project?
No.
Not quite, okay.
Easy, yeah.
Okay.
I know this for you.
So I guess, yeah, the next thing to do would be, to act, so I guess, so for some background, when you install, IDF, it downloaded a bunch of Python, code. And that Python code has been downloaded into the directory that you selected for installing, IDF. So now what you need to do is you need to, activate the virtual environment, that it created. And the way to do that is, so you need to find, so like in my case, it installed into just a default, which is my home directory /esp. Inside this, you should find, like the version name. Inside the version name, you will find ESPIDF. And inside ESPIDF, you will find this export.sh. And this export.sh will basically set up your environment. So I think on Windows, it's like export.bat, which is like a batch file. So what you want to do at this point is run this file. So you can do like // export.sh here, you can just give it the full path. And when I run this, it will like set up environment. Last questions? The command for what? So find this, so go into your ESP like installation path, which by default it's home directory /esp/version/ESPIDF. Inside ESPIDF, you will find export.sh. Or on Windows, it should be export.bat. And then you run this. So don't do /export.sh because like due to some reasons that will not work. But do /export.sh or like source space export.sh. Yes.
I don't know that. Are you like running Discord up to the problem? I don't know. Can you go back, ls that element. Okay, yes. So seeding, yes. Maybe start seeding. Yeah, that's. You just do like dark stuff. Sorry, like get your correct. Yeah, it's like seeding, all dark stuff. Okay, that's work. I don't know why it didn't work.
So whatever, what do you mean about?
Yeah, if anybody else has any issues, also let me know.